Hello, my name is Jonathan Moody, and today I will be talking about RSA matrix encryption. This is a modification of traditional RSA, which uses a matrix instead of a regular message to encrypt a message. So, to begin, we will talk about a basic overview of RSA and how it works, along with the actual mathematics behind how RSA works. Then we will move on to an overview of how the matrix encryption of RSA works, along with how the math behind that works. And then just talk about a couple basic uses for matrix RSA encryption. First off is just basic overview. RSA, as most of you will know, is an asymmetric key encryption, which means that the users will have separate public and private keys. Public keys are given out to be able to let other users encrypt a message for the receiving user. The receiving user will use their private key to decrypt that message to be able to read what the original plaintext was. The encryption is based off of prime factorization, which is difficult for current computers to be able to get through to factor prime numbers. Out of millions and millions of numbers, you're just trying to find the few in this, so it's harder for most cracking of passwords or messages to be able to be found. So that's mostly on that. Though there is speculation with the future foreseen to be quantum computing, that most of this kind of encryption will be made obsolete just based off of their speed, how fast it will be able to encrypt. Instead of taking hours or days or years maybe to encrypt, it may take a couple seconds, couple minutes. So that's how matrix RSA comes into play, which we'll talk about in a little while. So the basic math of RSA, you want to find two prime values. So for this we will use P and Q. The first thing you want to do is find an n value, which is P times Q. You'll use this later on. The next value you want to find is E, which will be relatively prime to n, or P minus 1 times Q minus 1. This will just find a number that's relatively prime to the other values that you found. D, which will be our decryption value later on, will need to be an inverse of E. So for your public key, in this case, for this example, is a combination between the n and e values, so your p times q along with your relatively prime value. Your private key will be the d value that we have, so that will be your just direct decryption value. For encryption, which we will use the value m, will just be m to the power of e mod n, which will give you your encryption value, or encrypted value. Your decryption value will be the encrypted value to the power of d mod n, which will give you the plaintext that you originally had, or the original sender had. So for an example, p will be equal to 7 and q will be equal to 17. Both of these numbers are prime, so they both fit into our values. The n value will be 7 times 17, which will be 119. So next we need to find something relatively prime, so we will subtract 1 from 7 and 1 from 17, which will give you 6 times 16, which is equal to 96. The e value that you found here, which will be your inverse value, is 5. So the d value here will be 77, which is equal to the inverse of e value to find that value. So you will do 5 times 77 mod 96, which is your relatively prime value, and this all has to equal 1. So the 77 will be the value that is found there. So the keys that you have for the public key is 119 and 5, and your private key is just 77. So for encryption, we will use just a value of 19 for this example. So here it will be 19 to the power of 5 mod 119, which will give you 66. So this is our encrypted value, or encrypted message. Decryption will be 66 to the power of 77, which is your private key that you'll use to decrypt. Mod 119, which is the 7 times 17 with the prime values, which will give you 19, which was your original value that you had. So next we will have just an overview of how RSA with matrices works. So in this, there's several different points of security, where originally you had just the public and private keys. You still have that here, but each time that you have a message of some sort, it generates a unique matrix that it will have. This just adds more decoding complexity, because along with that, you have to find both the public and private keys. You have to find the prime numbers that generate those, as well as how your message is generated in the matrix. It can be several ways depending on what size of matrix you want to use, how long the message is. Both of those can change the value. So along with this, the keys are larger, because this requires the use of the general linear group, which is a property within linear algebra that generates a prime number that can multiply a matrix. So because of this, it can take longer to generate a key, just brute force trying to break into it, which is also an issue trying to generate the key originally. It will take the computer longer to do the math to be able to generate a prime number. So for this example, we will use an actual A to Z message, but the corresponding letters will be matched through 1 through 26, since there are 26 letters in the alphabet. The message we'll use is cryptography, which comes out to this number that's on the screen right now. I don't want to say it, it's too long. So first we will pick some prime numbers. So we will go with some fairly large numbers. This may be something you might see not in top-end RSA uses, but just for this example, it's large enough for the example of what you might see. So P times Q in this is 250,997. So that will be our N value. It's the original part of the math is very similar to RSA, but the next steps are where it breaks off from RSA. So here you will calculate the f of n. So if you remember from a few minutes ago, to do this you do p minus 1 times q minus 1. For matrix RSA, because you're multiplying with a matrix, this prime number won't work properly. It will generate what will look like proper values, but whenever you do the final math for encryption and decryption, you will get something completely different than what you need. So for this, you need to find the general linear group, which will be p squared minus 1 times p squared minus p times q squared minus 1 times q squared minus q. This will generate the very, very large number that you see on your screen, which is just 3.9 times 10 to the 21st, without having to read off a very large number in detail. It's rounded, but if you have to have the full value to be able to encrypt and decrypt. If it doesn't, then you won't get the right value. So next you will need to pick your encryption value, which here we just picked 241. It's just a number that works. So the decryption value will be E times D mod F, or mod your previous value, which will equal 1. So here you need to find D. So here it will be 241 times D mod the previous number, the times 10 to the 21st number, which will then give you 1.01 times 10 to the 21st. So your public key will be N and E, which will be 250,997 and 241. Your private key of D will be 1.01 times 10 to the 21st. So your next step will be to first split your message into a square matrix. This is important, because without this, then the multiplication will become weird. It won't come out even whenever you want to regenerate your original message. So here you will need to do matrix multiplication on your matrix that you have to the power of 241 mod 250,997, which will then give you the matrix that you see on the screen now. To decrypt, you will need to take the encrypted matrix, which here is just 2 by 2. It was easier than doing a full large matrix for a longer message. To calculate this, you will need to use the power D mod n. So you will take your encrypted matrix to the power of 1.01 times 10 to the 21st, mod 250,997, which will then give you your original matrix that you had. And then here you can just plug it back in, just reorient all the numbers to the proper order, and you'll come out with your original message that you had before. It's a very large number. It becomes complicated, so it's much easier just to show the number than it is to show the whole math of trying to do it. So a few applications that may come up in the future. For right now, it isn't very useful. It takes too long to be able to run compared to regular RSA, which generating the numbers is just the two numbers multiplied together. Here you have to do 4 different equations all multiplied together, which will then give you the very large keys. But in the future, with quantum computing, this may be easier. So with the faster computing that quantum computers may give us, it may be able to generate the linear group faster that may be equivalent to just generating prime numbers for computers now. So, and also it may increase the speed of matrix multiplication. So it will overall increase the speed of matrix RSA, but it may get to a point where it will be more useful to use than regular RSA, which could get cracked fairly easily with a quantum computer. Now, if you want to use it right now, it may be useful for more private encryption if you have some kind of information that is sensitive or needs to stay permanently private other than the 2 people or 3 few people that need to see it. You may be able to use this. Even though it's slower, it's more secure with multiple points of encryption, so this allows for better security, more privacy, it stays confidential. So that may be a current use for it today. And I believe that is about it for this presentation. This was a presentation over RSA matrix encryption. Thanks for listening.